All right, so we're picking up where we left off with these chapter 15 practice problems, and we got all the way up to question 10 last class, and now we're going to start with question 11, and this is chapter 15, chemistry 3101. So question number 11 just asks us determine the multiplicity of each signal in the expected proton NMR spectrum of the following compound. So when it says multiplicity, that means the same thing as splitting. So this is where we apply the n+1 rule. All right, so I'm just going to ask you, what if I put all of these 9 protons in this tert butyl group in a box? What kind of splitting would I get for these? Well, the answer is I'm going to get no splitting for these because I have 9 protons, CH3, CH3, and CH3, right? So I have a total of 9 protons that are chemically equivalent. And the reason these are all chemically equivalent is because I have free rotation around this sigma bond. So there's no differentiation between any of these 3 methyl groups. And none of them are coupled to any protons, right? They're all equivalent, so they don't split each other. And they're all attached to this carbon, which has no protons on it. So if we do neighbors plus 1, or the n+1 rule, we get 0 plus 1, which equals 1, and therefore they are going to give us a singlet. We get a singlet for a tert butyl group, and that's true for any tert butyl group. If you remember when we were talking about different alkyl groups, a tert butyl group is actually one of the most recognizable groups. If you have a singlet that integrates for 9 protons, it's probably going to be a tert butyl group. All right, the next one is we have a methylene or a CH2 group here. Okay, so we have a CH2 group here. And, what are they next to if we do the n+1 rule? Well, one rule that I don't know if I went over with you yet, so I'm going over it with you now, is that generally speaking, protons are not going to be split by neighboring protons that are attached to nitrogen or oxygen, right? And that's because of the hydrogen exchange that I went over with you. And so it's not going to be split by this proton that I have in the green circle. And so if it's not split by that proton, and I look at this neighboring carbon, which has no protons next to it, that means that the methylene or the CH2 group in here, right, that's not going to be split at all. If we do n+1, yes, there is a neighbor. Yes, the one here in this green and red circle is a neighbor, but we don't get split by hydrogens that are attached to nitrogen or oxygen. So we end up with 0 plus 1, and we end up with 1, and so this is going to give us a singlet. The same thing with the hydrogen in the green circle. Any hydrogens attached to oxygen or nitrogen, so we'll put here H's attached to oxygen or nitrogen is going to give us a singlet. Okay, they always give us a singlet. And again, we went over that in the lecture slides as to why that is. Now, it gets a little more interesting out here on the left-hand side of the molecule. We have 3 protons here, right? We have this methyl group, so CH3. Now, could anybody tell me what the multiplicity will be for these 3 protons? Will it be a singlet, doublet, triplet, quartet? Could anybody answer that one? If I do n+1, what would I end up with for this one? How many next door neighbors does it have? These 3 protons in this methyl group. It's going to give us a triplet, exactly. Thanks, Kiana. So Kiana did this. n+1 is equal to 2 plus 1. Where did she get the 2 from? Well, it's from these 2 protons right here, CH2, right? So we get 2 plus 1, and that equals 3. Therefore, we get a triplet for these 3 protons. I'm going to skip the protons that I have in the black square for now, and I'm going to go over to, I'm going to put these ones in a purple here. So this methylene here. So the methylene in purple, we do the same rule. We have n+1. n+1 is going to be equal to 2 plus 1, right? Because these are the 2 neighbors. So we get 2 plus 1, which equals 3. And that gives us a triplet. So I'll just write here, triplet. All right, so now we come to the 2 protons that are in black. Well, you can see that they're split by a total of 5 protons. Right, they're split by these 3 protons and these 2 protons. And so we would say n+1. So for this one, we're going to say n+1 is equal to 5 plus 1, which equals 6. Therefore, we would get a sextet. I would accept that answer. I would say there's nothing wrong with that answer whatsoever. However, it's not entirely correct, okay? Sometimes it can be if the coupling constants between this splitting and this splitting, if both of the coupling constants are the same, didn't mean to do that. If the coupling constants are the same between the black and the blue and the black and the purple protons, then it will appear as a sextet. However, if the coupling constants are not the same, then it won't appear as a sextet. And if you're going, well, what are you talking about exactly, Mr. D? Well, let me show you. Let's go back into the slides here. So let me just find them here quickly. And no. So if we go into, no, that's not it either. Here we go. So if we go back into the lecture notes, and we covered integration and multiplicity. And one part that I didn't really go into a lot of detail was when we have a proton being split by two different protons. Let me just go over this with you kind of quickly right now. All right, so let's say, I'm going to erase all the spinach that I had on here from the last time. Let's say we're looking at this proton in red, and we're trying to figure out what's the multiplicity of this proton, right? We want to do the n+1 rule. Well, how many neighbors does it have? Well, it's got this neighbor down here, so that's hydrogen, so n+1. And we also have this proton down here. I'll put this one in black. Okay, so I've got the black proton and I've got the blue proton. So it might be a knee-jerk reaction to say n+1 is equal to 2 + 1, which equals 3, and therefore it's going to be a triplet. But in fact, this is not the case. Okay, you actually don't get a triplet here. And the reason why is because the coupling constant between the proton in red and the proton in blue, and the proton in red and the proton in black, those two coupling constants are different. And so instead of appearing as a triplet, this is the way you would think of it. You would say, okay, the proton in red is split by the proton in blue. That one, so if I write it down here in blue, that's going to give me n+1 is equal to 1 + 1, which equals 2. So that's going to give me a doublet. All right, and then we would do the same thing with the hydrogen in black and say, well, n+1, so I get, this one is going to give me 1 + 1, which equals 2. So that's also going to give me a doublet. So instead of giving you a triplet, it's going to give you a doublet of doublets. And you're like, well, what is that going to look like? Well, let me try and draw it out for you here. So if I put the ruler like this, okay, and we draw a line like that. So a doublet of doublets would look like this, right? A regular doublet would just look like this, okay? But a doublet of doublets would look like you've got one doublet, and then you have a second. Actually, that doesn't really look very good. Maybe it would look more like this. So you have one doublet, and then you have a second doublet. So it's kind of like two doublets in one kind of thing. And I might not be doing the best job at explaining this. So let me show you a very specific example here. Let's move on and cover these few slides that we didn't look at. So here's a very specific example that's shown in our textbook that will help us understand the whole idea of complex splitting, okay? So complex splitting, again, what I'm trying to tell you is that it results when a proton is split by two different kinds of neighboring protons. So if we're focusing on HB, okay, these two protons are chemically equivalent. How are they going to be split? Well, they have three neighbors in red, right? So 3 + 1 gives you 4. So we'll write here 3 + 1 = 4. So that would give you a quartet. And the two protons in green, okay, so for that one, I'll just write it in black. I have 2 + 1, which equals 3. So that would give me a triplet. And so what you're going to end up with is a quartet of triplets or a triplet of quartets. And you can see here that this is a quartet of triplets. Okay, so we have 1, 2, 3, 4 signals for our quartet, but each one of them is split into a triplet. This is a triplet, this is, and this is. And again, the reason why is because the two coupling constants are different. And you can see here that in this specific example, what they're saying is that the coupling constant between A and B is much bigger. So you see the distance between the middle of the peaks, right? So between A and B, I'll just do it like this. You can see the distance between these is much larger. So this is JAB, the coupling constant between A and B. And then in between here, all these little tiny gaps here and here, that is JBC. Remember that J just stands for coupling constant, okay? So let me write that in here. J is equal to coupling constant. All right, so we get a quartet of triplets in this case. However, you could get a triplet of quartets, and that's what's shown here. So this is a triplet of quartets. Why do you get a triplet of quartets this time? It's because they're saying, okay, well, the JBC, the coupling constant between B and C, is bigger than the coupling constant between A and B. And then sometimes, if the two coupling constants are similar, then we just end up with a whole multiplet, right? Which is very difficult to tell what's going on. So this we just call a multiplet. And you know, if you're wondering, well, can I call everything a multiplet? No, you can't do that. All right, so there you go. So that's a little bit about complex splitting. And then just one more time, I want to review how some protons are not split. So it says the protons bonded to carbons split each other, but the protons that are bonded to a hydroxyl, so those are not split. So if you have an OH group, okay, if you have ROH, this hydrogen is not going to be split. So we'll write here, not split, okay? The hydrogen on an alcohol, and we covered the reason why. It's because they undergo rapid exchange. So again, it's kind of like trying to take a picture and you don't see the effect of the shielding and the de-shielding. So we usually get a broad singlet if we have a hydroxyl proton. So there we go. So that's a little bit of review and a little kind of introduction, I guess, to complex splitting. So let's get back to the problem here, which was this problem. And so, the protons in black, what would it be? It would either be a quartet of triplets or a triplet of quartets, right? Because you're coupled next to 3 and 2 protons, like I showed you in that example on the slide. But if you said a sextet, you said 5 plus 1, I would totally accept that at this level. All right, let's move on to the next one. It's the same kind of thing. It says determine the multiplicity of each signal in the proton NMR spectrum. So let's see here, 1, 2, 3. So another rule that I wanted to go over with you this morning is that aldehyde protons are not split. So we'll put here aldehyde protons are not split, right? Because you can see that this hydrogen is, let me use a different color here, is 3 bonds away from these 2 protons that I'm writing in blue here, but it is not split. That is a rule that you need to know. So I'm just going to put a star by that and say this is a rule that aldehyde protons are, generally speaking, not going to be split. So this will not give you a triplet because the neighboring carbon has 2 protons. All right, and they also don't split protons. And so if we look at the 2 protons in blue, so let me just remove this and I'll just make it a little smaller here. If we look at the 2 protons in blue, okay, what kind of splitting are we going to see for these 2 protons? How many protons are they coupled to? Well, they're only coupled next to this 1 proton here. So we end up with n plus 1, which is equal to 1 plus 1, and so we get 2. So those 2 protons are going to give us a doublet. But if I put this methyl group, these 3 protons in black, could anybody tell me what the multiplicity would be for those 3 protons? And it's not a trick question or anything. Could anybody tell me the multiplicity of these? Thanks, Ariane. It's going to be a doublet, isn't it, right? So we get n plus 1 is equal to 1 plus 1, which equals 2. Therefore, we get a doublet, exactly, for the 2 black protons, because they're only split by the proton in green. Now, the proton in green, so with the proton in green, I'll use red, and I'll circle the proton in green. This one's a little more interesting, isn't it? Because if we do n plus 1, well, how many neighbors does it have? It has a total of 5 neighbors. And so you would say 5 plus 1, which equals 6, and so it would give you a sextet. And I would accept that, okay? I have no problem with that. However, it's split by 3 protons and 2 protons, and if the 2 coupling constants are not different, are different, you would get a quartet of triplets or a triplet of quartets. Again, for this class, if you write sextet, if you assume the coupling constants are identical, that's totally fine with me. But anyhow, I just wanted you to be reminded of that. All right, let's move on to these 2 protons here, this methylene. Could anybody tell me what the splitting would be for these guys? N plus 1 is equal to, what would I get for these 2 protons? Anybody? Yeah, for this one I get a singlet, right, Kiana? It's 0 plus 1, there's no neighbors, so I get a singlet. There we go. And then the 9 protons in the tert-butyl group, of course, that's going to give us a singlet. So we get n plus 1 is equal to 0 plus 1, which equals 1. And so we get a singlet for these ones. All right, a little practice on coupling constants, a little more practice on the n plus 1 rule. You can see I got a lot of information written on there. Anyhow, let's move on to question 13. Let's do this one kind of quickly. It says, how would you use proton NMR to distinguish between the following compounds? Well, the first thing you probably notice when you look at the problem is that each one of these molecules has a plane of symmetry in it, doesn't it? Right? And remember that identical protons are not going to split each other. Okay, so let's start with the 2 methyl groups on the end of this one here. So we have a methyl group here and a methyl group here. Those are identical, right? What kind of splitting are we going to get for those? Well, they're both coupled next to 2 protons, right? So that means for the protons in blue, we're going to see a triplet. So we'll see a triplet for, oops, let me use blue pen. We're going to see a triplet for those, okay? So triplet, we could write here too, triplet, okay? It's the same triplet, but anyhow, the protons in red, for those, what would we see? Could anybody tell me what kind of splitting we would see for the protons in red? And it's not a trick question or anything. Yeah, exactly. We're going to get a quartet for those. So I'll put here quartet. Okay. And the reason I write the word quartet out is because you don't want to mix it up with quintet. Anyhow, and then the protons in black here, those aren't split by anything. And so for these, we're going to see a singlet. Okay. So we see 3 signals in the proton NMR, right? We see a quartet, a triplet, and a singlet. Okay. Let's take a look at number 2. In number 2, oops, let me get my black pen out here. This methyl group and this methyl group, they're not coupled next to anything. So we're going to see a singlet for those. Then I have these 2 protons and these 2 protons. They're each split by 2 protons. And for those, we're going to see triplets. So I'll just put triplet here and a triplet here. Now, if I circle these ones in blue, and I'm going to erase the line here, my plane of symmetry. Well, how many protons are these split by? They're split by a total of 4 protons, right? They're split by 2 protons here and 2 protons here. So 4 plus 1 gives us 5. So this one is actually going to give us a quintet. And it's going to be a quintet because the coupling constants would have to be identical because of the symmetry in the molecule. And so the only way that you would tell the difference between the two, because you get a quartet, or sorry, you get a triplet and a singlet in both of them, is that one gives you a quartet that integrates for 4 protons, and the one on the right gives you a quintet that integrates for 2 protons. So, I mean, you could write it any way you want, but I would just say this compound, so number 2 gives a quintet with 2 proton integration. Okay, and if you wrote number 1 gives you a quartet with 4 proton integration, I would accept that too. All right, let's get a little practice on our chemical shifts here at number 14. It says, how would you use proton NMR spectroscopy to distinguish between the following compounds? Well, if we look at the 2 compounds, they both have an aromatic ring, right? And you're going to have 5 protons in the 6.5 to 8 part per million region, right? Same thing here. So you can't use that to differentiate between the 2. You're going to have 5 protons in the 6.5 to 8 ppm range. Then if we look at the isopropyl group on each, right, you can use that to distinguish between the 2. Because if you look at the methine here, that's going to give us a septet, right? Septet because of n plus 1, 6 plus 1. But what's the chemical shift going to be? We'll put here septet at. We start with the baseline for a methine, which is 1.7 parts per million. And how many are we going to add if it's attached to this oxygen that I have in red? Could anybody remind me of that? You might have to go back to table 15.2 or table 15.1. I think it's table 15.1. I get the 2 mixed up. But how many parts per million do I de-shield it? How much further downfield does this go if it's attached to that oxygen of an ester? Could anybody tell me that? Yes, thank you, Kiana. It's 3, isn't it? 3.0 ppm. And so I get a septet at 4.7 parts per million. Whereas in the other one, here, my septet, I get septet is going to be at, so we start with 1.7 parts per million. And since it's alpha to the carbonyl, we only add 1 part per million, 1 ppm, and we end up with 2.7 ppm. And so that's how you would differentiate between the two. The number 1 has a septet at 4.7 parts per million, and number 2 has a septet at 2.7 parts per million. You could also differentiate between the two of them using the doublet for the isopropyl methyl protons. So you could use these protons, okay, and these protons to differentiate, but the difference in the chemical shift is not going to be as great as the two septets. So if you use that, it's okay, but again, the difference is not going to be as great, right? Because you only use 1/5 of the 3.0. Anyhow, so let's move on from there. 1/5 of 3.0 in the first one and 1/5 of 1 in the second one. All right, anyhow, I digress. Let's take a look at the next one here. It says a compound with a molecular formula of C9H10O2 has the following proton NMR spectrum. Which is of the following structures is consistent with the spectrum? So let's see here. What's the first thing we could do? We could calculate the HDI. So there we go. So we could calculate the HDI. Did anybody get an HDI for this one? I got an HDI of 5 for this one. And you notice that every single compound has an aromatic ring and a carbonyl. So we the HDI doesn't really help us all that much. So it's an aromatic ring, which has 4, and then a carbonyl, okay? And they all have that in the structure. All right. Now, you notice that every single one of these is a monosubstituted aromatic, right? So they all have 5 aromatic protons, and these are the aromatic protons because they're in between 7 and 8 parts per million. So that means that the height of the step curve here, this represents 5 protons. Now, if that represents 5 protons, can you just eyeball it and say, well, how many protons must each of these represent? Okay, because if you zoom in here, you get 2 triplets. We have a triplet here and a triplet here. Could anybody tell me how many protons each one of these triplets represents just by eyeballing it? If this distance here, yeah, thanks, Ariana, absolutely. If this distance equals 5 protons, right, that would mean that this distance here is pretty dang close to 2 protons, right? And this distance here would be pretty dang close to 2 protons. So if we have 2 protons and 2 protons that are both triplets, maybe you remember this from the other day, but the only scenario is that you have 2 methylenes like this, and they're attached to different groups, X and Y, right? If they're attached to different groups, then they're going to be in different electronic environments. So that means that this one will give you a triplet and this one will give you a triplet. Now, let's just quiz you with one more thing here. How many protons are represented by this step curve here? Anybody? I know you know the answer. How many protons here? It looks like it's about half the height of the 2 protons, right? So this is 1 proton. Well, we have a chemical shift that's greater than, it looks to me, if this is 12 and this is 11, let's say, or sorry, 13, to me it looks like it's around 12.2 parts per million, maybe. If you go back to the table that we used before, okay, and you look at the chemical shifts for protons, the only thing that's going to have a chemical shift of around 12 is going to be a carboxylic acid. So that simplifies the problem greatly. If we go back here, okay, and we look at all of these compounds, this is not a carboxylic acid, this is an alcohol, this is an ester. The only one that's a carboxylic acid is number 2. So the answer has to be number 2, and you see that it works out perfectly, right? We have the 5 protons on the aromatic ring, and then we have the 2 methylenes, and then we have the carboxyl group. So before we move on to the next problem, I want to show you one thing, and I know that many of you are taking the lab right now with Mr. Geiger, and if you're doing that, he's probably going over annotation, but I just want to review annotation with you quickly. And it's the proper way to label an NMR spectrum to prove that you know what the structure is. So I'm just going to delete this for now, and I'm going to redraw this compound. Okay, so I'm going to redraw this compound. Just going to look like this. So we get 2 methylenes, and there's our carboxyl group, like this. So the way that you annotate a spectrum to prove that you know what it is and that you've identified what each signal represents is you start on the right-hand side and you use the letters of the alphabet. A for the first signal, B for the second, C for the third, and D for the fourth, right? We have 4 signals, so we use the first 4 letters of the alphabet, okay? And this is a standard. We always start on the right, A, B, C, D, heading left. And that way, everybody who annotates a spectrum should always end up with the same answer. So now what we do is we write the corresponding letter next to the corresponding proton. Well, let's start with the easiest one, which would be D, right? We know that the proton of the carboxylic acid is D. Now, if we look at A and B, these must be these two methylenes in here. So which one is going to be B? Which one would be more D-shielded? Do you think it's the one in the red circle or the one in the blue circle? Which one of these is going to be more D-shielded? Well, the one in the red circle is attached directly to a carbonyl, and we know that a carbonyl is very electron withdrawing. And so I would say that B is probably going to be these 2 protons, which would mean these ones would be A. And since we have a multiplet here, this is a multiplet, all you have to do is write C next to all the aromatic protons, and that's close enough. All right, so that is how you properly annotate a proton NMR spectrum. And I'm sure you're getting more practice with that in the lab. All right, let's move on to number 16. Another question about how many signals would you see in the in the carbon-13 NMR spectrum of this compound? Well, do we have free rotation around this bond? The answer is absolutely. Right, so if we have free rotation around that bond, that means that in the aromatic ring that these 2 carbons would be chemically equivalent and these 2 carbons would be chemically equivalent. Then we have the 2 quaternary carbons. We have the one in yellow. It's kind of hard to see, but I put a yellow circle right here. And then we have the one in green down here. Okay, so in the aromatic ring, we have a total of 4 carbon signals. Now, if we look at all the carbons in the other part of the molecule, so if I put this one in red, this one in blue, this one in green, this one in black, and maybe this one in yellow, are any of those carbons chemically equivalent? The answer is no. None of those carbons are chemically equivalent. And sometimes students will want to say, well, the one in black and the one in yellow are chemically equivalent. No, they're not, right? Because you can see that the carbon in yellow is trans to the aromatic ring, but the carbon in black is cis to the aromatic ring. So they are not chemically equivalent. And so that gives us a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 signals, right? Because remember, the one in blue and the one in red in the aromatic ring, those are chemically equivalent. Give me a thumbs up if you follow me on that one. Is everybody with me on that idea? And again, stop me if you have a question. I'm more than happy to go over the problem the second time. Okay, so that's how many signals we see there. The next one, I didn't really give myself a lot of room to answer this, but it just says how many signals are there in benzene. So if we draw the structure of benzene up here, okay, it's got a total of 6 protons. So I'll scribble them all in here carefully. All right, so we have C6H6. So it might be a knee-jerk reaction to say, well, I'll just look at this proton, 1, 2, 3, therefore it's going to be split by this. But remember that protons that are chemically equivalent do not split each other. So let's scribble that down. We're only going to get a singlet, so we see one singlet, because protons that are chemically equivalent do not split each other. It doesn't happen. There's no splitting. Okay? So for benzene, all you would see is one singlet. It's the same thing with cyclohexane. If you were to look at cyclohexane, which is C6H12, right? C6H12. The only thing you would see here is one singlet because every proton is chemically equivalent and therefore there's no splitting. So this is actually a rule that you have to memorize. Protons that are chemically equivalent do not split each other. All right, number 18. I love these ones where you have to go through every single compound to get to the to get to the answer. Anyhow, which of the following compounds is going to give us 5 signals? So we're looking for 5 signals in the carbon-13. So if we look at the first compound, number 1, you can see that there is a plane of symmetry through the molecule right here. And so if we identify all the carbons, this is a unique carbon, this is a unique carbon. These two are chemically equivalent based on symmetry. These two, I'll use my blue, these two are chemically equivalent. And then I have this one, which is unique. So we have a total of 1, 2, 3, 4, 5 signals. So I hope this is the answer. The answer better be A. Could anybody tell me how many signals you would see in number 2? How many signals would you see in this one? Anybody have an idea about this one? Yeah, Kiana says 7. I agree with you, Kiana. There's no symmetry in this molecule whatsoever. No symmetry. Therefore, you'd see 7 signals, right? And in the next one, there's no symmetry either. So no symmetry, therefore 7 signals. Actually, that applies to all 3 of the remaining compounds. Okay, all 3 of these, there's no plane of symmetry in any of these. And so each one of these is going to give you 7 signals. All right, so a little practice on identifying a plane of symmetry in that one. Let's try one that involves a carbon-13 spectrum. So it says, which of the following compounds is consistent with the carbon-13 NMR spectrum shown below? Remember that all the signals that are below 100, those are usually sp and sp3 hybridized carbons. And then anything above 100, generally speaking, is going to be something that's sp2 hybridized. And we said that the carbons in between, what was it, around 100 and 150, something like that, those are going to be aromatics. So all of these signals here, these are going to be aromatic. There we go. And then if we have a signal that's around 200, that's going to come from a carbonyl. So we've identified that, and we haven't even counted up the number of signals that there are. So let's count them up. We've got 1, 2, 3, 4, 5, 6, 7. So we have a total of 7 signals. Okay, in our carbon-13, we have a total of 7 signals. Now, if you look at each one of these compounds, it has more than 7 carbons. Right, if we look at the first compound, it's got 6, 7, 8, 9. So this one has 9 carbons. This one has 6, 7, 8 carbons. This one has 6, 7, 8 carbons. This one has 6, 7, 8, 9 carbons. Okay, so now let's figure out how many signals we would see in each one of these. So let's just erase all that and we'll figure out the number of signals. So if I look at the first one, you can see that there is a plane of symmetry here, right? Because you have free rotation around this carbon-carbon bond right here. And so how many signals would we see for this guy? We'd see 1, 2, 3, 4, 5, 6. Maybe I should use a different color here. I'll use purple. So 6, and we'll put 7 over here. So we have a total of 1, 2, 3, 4, 5, 6, 7. So 7 signals. So this one is in the running. So we'll write here 7 signals for this guy. If we go to the second one, well, that can't be one of the options because it doesn't have a carbonyl. So we can scratch that one off. We'll put here no carbonyl. Same thing with number 3, has no carbonyl. And then if we look at number 4, how many signals is it going to have? Well, let's see, there's no symmetry in it. So we'll scribble down here, no symmetry. Okay, therefore it's going to have a total of what? 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'd get a total of 9 signals for this compound. So 9 signals. Therefore, this cannot be the correct structure. The correct structure has to be number 1. Give me a thumbs up if you're with me so far on this problem. I wanted to try annotating it with you. All right, cool, cool. Good, so let's practice our annotation skills. So let's put this compound like this. So we're just redrawing the compound. So this would be paramethylacetophenone is what you would call this compound. It's kind of at a weird angle. Maybe that's a little better. Something like that. And there we go. All right, so now we're going to label the peaks A, B, C, D, E, F, G. Well, we can see that this one is G. And as far as E and F go, these are the two aromatic protein or carbons that there's only one of, right? Since D and C are twice the height, right? Since D and C are twice the height, those are probably the ones that have the symmetry, right? The ones that I have highlighted in red and blue in the structure. Well, D is more deshielded, so it's probably closer to this electron withdrawing group because there's a dipole going this way. So I'm going to put D for these ones. Then I'll put C for these ones. I'll put F for this one because it's closer to an electron withdrawing group, and E for this one. Then we have B and A. I would say that B is probably the one closest to the carbonyl because it's more deshielded. And then you have A down here. And again, that's my best guess at annotating this, but that's just kind of giving you an idea as to how you annotate a carbon spectrum. Let's move on to number 20. Which one of the following compounds is consistent with this carbon-13 NMR spectrum? So let's take a look here. We've got a total of 3 signals. We've got A, B, and C. So we've got 3 signals. And now we could just kind of go through these compounds and figure out which one has 3 signals. Well, you see that in the first compound, there's no symmetry whatsoever. So this one is going to have 5 signals in the carbon because there's 5. That's kind of bad handwriting. I'm going to try it like this. 5 signals because there's no symmetry and there's 5 carbons in the molecule. How many signals would I see in number 2? Could anybody tell me in this one? There is some symmetry in this molecule. It's not abundantly clear the way it's written, but anybody have an idea about this one? Well, if we take a quick peek at this one, we see that we have a unique carbon here, 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 but these 2 methyl groups are chemically equivalent, right? Because we have free rotation around this bond here. And so for this one, we would see 4 signals. Okay, if we go to number 3, we have a unique carbon here, 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 but these 2 are chemically equivalent, so we'd see 4 signals in this one as well. So I'll put here 4 signals. And we've got a plane of symmetry, or an axis of symmetry, I should say, here of rotational symmetry. And this compound, and so this one's only going to give us 3 signals. These 2 methyls are chemically equivalent, these 2 methylenes are chemically equivalent, and this methine is unique. So the last one gives us a total of 3 signals. So we'll put here 3 signals, like that. So if I redraw the compound on here, okay, like this, and I want to annotate it, the carbon that's going to be the most deshielded by far is the one that's attached to the oxygen. So we have C. The one that's least deshielded is the one farthest away from the oxygen, and then B would be the one that's somewhere in the middle, like that. All right, let's keep going. I think this is the last problem. Yeah, this is the last one here. And this one we have to use a lot of data to try to figure out the problem. No, sorry, there's 2 problems. Sorry, my mistake. Okay, let's try number 21. Which one of the following compounds is consistent with this carbon-13? So we've got a total of 1, 2, 3, 4 signals. We looked at the same thing in the last problem, so we kind of already solved this one in a way. This one has 5 signals. Oh, no, we didn't, because these 2 both have 4 signals, don't they? So if I go here, 1, 2, no, sorry. It's not the same compounds. This one has 4 signals. So 1, 2, 3, 4, yeah. So here we have 4 signals, and this one was in the last problem, and this one has 3 signals. How many signals does number 2 have? in the carbon? Could anybody answer that? Exactly. Thanks, Ariana. I have 3. Exactly. So Ariana says, well, this is unique. This is unique. But all 3 of these methyl groups on this tert-butyl, those are all chemically equivalent. Okay, this is actually not a tert-butyl, but anyhow, it doesn't matter. It looks like a tert-butyl. So this one has a total of 3 signals. 3 signals. Therefore, the answer has to be number 3. Okay, this has to be the correct answer. So if we try annotation again, we could redraw the compound like this. And D is the most D-shielded, so that would have to be this one here. Then we have B and C. Well, whenever you have an alkyl group that's might have more of an electron withdrawing effect, and so for this one, I would put C would be more D-shielded and B would be B would be less D-shielded, and then A would have to be these 2 here. Again, if you mix these up, if you put B or C or B, I wouldn't think it's that big of a deal if you mix those up. It's not the end of the world. Well, let's figure out the last one here. It says you've got a compound with a molecular formula of C5H10Br2, and so it's got an HDI that's equal to 0. It gives you the following carbon-13. So this one here is your regular broadband decoupled. So this is just your normal spectrum down here. This is your regular everyday carbon-13 that gives us all the signals. This, by the way, is solvent. So this one here is this is deuterated chloroform. So this is just the solvent. So don't worry about those 3 little peaks there. But anyhow, so we see that we have a total of A, B, C. So we have a total of 3 signals in the compound. Then in our depth 135, remember the depth 135 shows all the CH2s going down, right? Pointing down. I'll put here down. And so that means that every single signal in here is a CH2, right? Because they're all pointing down. And then in the depth 90, we see the methynes and the in the methyls, and there's none of those in there. So there's also no quaternary carbons because there's nothing that disappeared when we went from here to here. Every signal is still there. So everything is a CH2. So all methylenes in this compound. And then we have an HDI of 0, but we've only got 3 signals. So that means there must be symmetry in the molecule. All right. You also notice that the height of C and B is about 2 times the height of A. And so that means that C and B probably correspond to 2 types or 2 CH2s, and A corresponds to 1. So if you're confused about what I'm getting at here, what I'm saying is this, is that C probably represents 2 CH2s, B probably represents 2 CH2s, and the A only represents, use a red pen here, only represents 1 CH2. And then I have 2 bromines, so how would I put that together? Well, there's only one way to put all this together, okay? And that's going to be to have something that looks like this. So we have CH2, that's attached to our 2 methylenes in blue. I'm maintaining my symmetry here. Then these are attached to the ones in black. Where's my black pen? Here we go. Like this and like this. And then we put our 2 bromines out here like this. There we go. So the one in the middle is A. These 2 are going to be B, and these 2 are going to be C. The reason I put the ones that are the most deshielded in black is because those are attached to the bromine, and bromine is an electronegative element. And so there you go. We've solved every single problem in the problem set.